And I'm going to share my screen. All right, you should be able to see my screen now.
Yep.
Cool. Is it big enough for everyone to read?
Yeah, I can read it. Do you have it
Okay,
in
cool.
presentation mode or?
No, I'm just doing it in Google Chrome.
Oh, okay.
I
Then
can
yes,
see.
we can.
All right. So I guess we can go ahead and get started. So for the recent updates, we've recently added the ability to load data from Happy servers. So we've released an initial load routine, and it's happy. So it's the happy function inside the happy file, inside the happy folder. And the routine is essentially just a wrapper around Bob Weigel's official happy client package in Python. So it uses that to actually go out and access the data, and then it saves the data in PiPlot variables. And the development is occurring on our master branch under PiSpeedus. And just as an example, we've recently developed access to swarm data using Happy. So we have a new load routine for accessing swarm mag data that uses their Happy server, which is available at, it's under the swarm folder. And we have a crib sheet showing basic usage of this under the PiSpeedus examples repository on our GitHub page. And this is mostly a template for future Happy developers right now. I think the Swarm has other data sets available other than Mag, but not available on their Happy server, at least when we initially developed this. But I think this would make a really good template load routine for missions that are hoping to distribute their data from Happy. And the Swarm, one thing to note is the Swarm team actually has an official Python client for their data. So you should be able to use that to access all of their data sets. And actually, you should be able to use that and then easily save the data in PiPlot variables as well. But you'd have to do that external to PiSpeedus. But we can, I was actually thinking about putting together a few more examples using the official team Swarm client to access the data and then saving it in PiPlot variables. But we're not there yet. So here's an example of the Swarm load routine. It matches the general format of the rest of our load routine. So it's just PiSpeedus.mission.instrument. So PiSpeedus.swarm.mag, and give it the probe, the time range, and the data type. I think it supports the LR data as well as the HR data. So it goes out internally. It just uses Bob Weigel's client to access the data sets and then loads them into PiPlot variables. And then you could just call tplot, the tplot function on the variable you want to print or plot, and it creates a plot of the B field in this case. And we also added the latitude and the longitude along the as secondary x-axes. So you can see the latitude and longitude are plotted alongside the B field. We've also recently added a wrapper around the Geopath library. That's the pure Python implementation of the Geopath library. So we can now generate the B field at a series of locations using T89, T96, T01, and the TSO4 B field models. And we have more examples on our documentation. So PiSpeedus.readthedocs.io. And it should be right on the side there. So on your left-hand side, there's a magnetic field models. And this has copy-paste examples for each of the field models to show you how to use them, including the TSO4 and the full generate using the solar wind to actually generate the calculate the plasma parameters required for the input to the model. So just as an example for T89, you just load some position data. In this case, we're loading MMS ephemeris data, and then you import the TT89 model, run it on your, call it on your position variable, and then it just creates a new tplot variable with underscore PT89 at the end for the 89 model. And then you can plot it. So you just call tplot on that, and it should create this figure, which is a plot of the B field at the spacecraft location using the T89 model. See, we've also had a recent contribution of the spherical elementary currents and the equivalent ionospheric currents routine. So this allows you to load the data as well as create plots of the spherical elementary currents and the equivalent ionospheric currents. This was provided by a couple of researchers at the University of Colorado Boulder. The one thing to note is that it requires the matplotlib base map toolkit, which I think is easy to install on Windows and Linux, but it's more of a hassle on Mac, which is why we're not installing it automatically. And development's occurring under the SECS folder in PiSpeedus. We also now have several general routines for doing particle calculations from the distribution function data, including we can now calculate moments. That's using the same algorithm that we have in IDL. We could also generate energy spectra and angular spectrograms, including pitch angle distributions and gyrophase distributions. And we're working on developing 2D slices now. This is the 2D slices is by far the most requested feature in PiSpeedus. I get that every couple of weeks now, someone asking about that. So that's the big feature that we're developing right now. And I mentioned earlier that we have PiSpeedus.readTheDocs.io. So we're now generating these docs automatically using Sphinx, triggered by commits to the master branch. And we now have over 100 copy paste examples. I showed the T89 one a second ago. I can show. So if you just click load routines on the left-hand side, you can go to one of the missions, say for instance, cluster, and you have documentation for the instrument, and then you have a copy paste example that should just generate a figure. So in 4 commands here, we load the cluster FGM data and then create a plot of it. And we have these for most instruments across all of these missions now. And so another big update is that we now have we're working on a matplotlib backend to PiPlot. So essentially it's PiPlot, but just using matplotlib to generate the figures instead of Qt. So this allows for publication quality figures. So in addition to save P and G, we now have save EPS for encapsulated postscript, save SVG for vector graphics, save PDF for PDF files. This also allows us to now generate the figures in Jupyter notebooks, including like Google Colab, DeepNote, Jupyter Hub. And this also adds an option to return the figure and access objects. So users can directly manipulate their figures, and they can then add text, images, make whatever changes matplotlib allows. This also adds the option to add error bars to line plots, set just like we do in IDL by setting the dy option when creating the variable with store data. And it also adds automatic interpolation options for spectrograms. So this was requested by one of the instrument teams on MMS. And there's much more. There's a lot more going on there. We recently, like just last week, I added the ability to highlight intervals and add text without actually returning the plot and figure objects, just with an annotate function. So see, I'm now using Google Colab to develop a bunch of examples. So we now have over 30 notebooks showing how to analyze MMS data. We also now have a coordinate system transformation notebook, a notebook for working with, showing how to work with dates and times with PiSpeedus and PiPlot. And I have a great big notebook called Exploring the Heliosphere with Python that I've been working on. And this starts at the sun and then goes all the way to the ground, showing data all the way from the sun to the ground. It includes some Senpai data first of the actual sun, and then it loads Parker Solar Probe, Solar Orbiter, and a bunch of other missions. The one thing to note is the Parker Solar Probe and Solar Orbiter data have different example dates from the other missions. But for everything other than Parker Solar Probe and Solar Orbiter, the data is from March 2017 from the same event. And that's available in our, it's both available on Colab and it's available in our PiSpeedus _examples repository. And so plans for Wednesday's hackathon. So my plan for Wednesday's hackathon session for PiSpeedus is to develop a bunch of PiTplot examples. And I was going to use the IDL example crib sheets. We have a whole bunch of IDL crib sheets for essentially just scripts that show how to do a bunch of stuff with IDL tplot. And I was hoping to move those over into Python. So for the latest version, using the latest version of PyTplot. So with the matplotlib backend, essentially recreate a bunch of those crib sheets, as many as we can. And looks like we have chat. So there was a question about any effort to incorporate Swarm Team's Python client as PiSpeedus. Not yet. I was thinking about, initially I was thinking about creating some Jupyter notebooks on Colab that just use PiSpeedus and PyTplot alongside the Swarm Team's Python client to actually load the data into PyTplot variables. I think that's really the first step to essentially the first step to actually making that integration. But that's pretty much all I have. Any other questions?
Rebecca.
That was my question. Following up, so the motivation for that question is basically the whole discussion about getting these missions, the specialized packages developed by missions, incorporated into other longer term packages for stability, right? So have you thought about contacting them to like take their Python client and pull it completely into PiSpeedus instead of trying to imitate it? Like you would just alter their package a little bit, as little as possible, and then just pull it in for long-term maintenance purposes.
We have not.
Is that something that you think is appropriate for PiSpeedus, or would you roll that on to say PySet or some other package?
Well, I'm not sure if bringing it, actually making it part of PiSpeedus would be good. I think keeping them independent is probably best because I mean they're going to be really good at load access to their data sets, and we're going to be really good at essentially providing a wrapper around that. So instead of packaging it up with PiSpeedus, what we would do is add it as a dependency, and then just like we're doing with the Happy client. We don't package it up with PiSpeedus, but we do require it to be installed and then reuse it.
Right. That still begs the question of what's going to happen to that capability when their mission funding ends. Maybe at that point, it'll be a good discussion to have with them.
Yeah.
Any idea when their mission funding ends? Just for the sake of thought.
I don't know, but I think they're on this call.
Oh, well, then maybe they can answer the question.
Pete, I see you have your hand up.
Yeah, so Pete
yeah, so it's going to be a different question, Eric. It was about the Happy support. So if you're supporting the Happy client, where you already provide a native way of reading in certain data sets, and Happy also provides that same way, how does that process work? Are you only encapsulating the Happy calls when it's a new data set, or does the user get the choice?
So our Happy client is really just a wrapper around the official Happy client. So essentially, you cause the official Happy client to load the data into NumPy arrays, and then we take those data and then create tplot variables from them.
Okay, so I can continue to use PiSpeedus for everything that it supports, and then just use Happy where it's something novel.
Yes.
Okay, all right, that makes sense.
And then you asked about the bleeding edge matplotlib backend. So
Yeah.
the way to install that right now is to install it directly from the GitHub page or from the branch. So for instance, in this Exploring the Heliosphere with Python notebook that I showed at the very top, I installed the bleeding edge. So it's really just the repository and then archive, and then the archive under the archive folder, it's the matplotlib-backend zip file.
Okay.
So
All right,
there's
I'll
an
get that
example at
played.
the top.
Yep. Thanks.
Yep.
Any other questions for Eric? If not,
Can I ask one more question since I forgot to lower my hand?
no worries, go ahead.
On the when you're calculating the moments, it seems pretty straightforward for density and velocity, but there's some nuances with temperature calculations. Do you provide like a standard way of doing that, or is there a way for the user to specify some variations in how that's integrated?
So for right now, what we did was translate over the exact IDL code that we have for generating it. But it's not very flexible. I think there's also some assumptions made in there. So you would have to work with us to actually get your the data products that you want to make sure that they're actually working.
Okay.
The idea is that we have these general routines that we plotted or that we ported over from IDL, and those general routines are going to be are essentially we're going to write wrappers around those routines to actually use them. For instance, we have a MMS part get spec routine, which generates the moments for MMS. And eventually there's going to be a them part get spec that generates the moments for themis. Because otherwise you would have to actually figure out the format of the underlying distribution functions and get them into the correct format. And then you have to check various assumptions, like how angle or how energies change with angle. So it's more involved than just calling the routine at the moment.
Yeah, understood. Okay.
Any other quick questions for Eric?
Thanks for listening.
Thanks, Eric. All right, next up, I believe we have Nick presenting a Plasmapi update.
Yeah, that sounds about right. I'll share my screen. And is my audio okay?
Yeah, I can hear you.
Awesome. So yeah, so thank you, Julie, for all of your hard work in organizing this meeting. We very much appreciate it, and I really enjoy these meetings too.
Thank you.
So today I'm going to give an update on Plasmapi. All right, so to start off, I wanted to give a really high-level view of the Plasmapi project. The mission of the Plasmapi project is to grow an open source software ecosystem for plasma research and education. And it fits kind of a strange area with PyHC because we want to be like part of we're working to be part of the PyHC ecosystem. And we also want to have an ecosystem also that includes a lot of things regarding laboratory plasma science and then fundamental plasma science and things like that. Right, so the central part of our software ecosystem is the Plasmapi core package. And the idea in that is to include the most frequently needed functionality. And it's currently under active development. And we're hoping to release version 0.8 approximately 1 month ago. But hopefully it'll happen like in the next month or two. We're also hoping to have affiliated packages that will contain more specialized functionality. And those are more to be created by the broader community. And this is based on the AstroPi and SunPi models. We also want to create a bunch of educational resources to introduce plasma concepts using Plasmapi. And we're also big into growing our community. So we have weekly online community meetings, as well as working group meetings and office hours. And we also have a code of conduct. I want to give a very brief introduction to two of the sub-packages that you'd first encounter when using Plasmapi. The first is plasmapi.particles. And in that, we have a couple of classes that can be used to represent either single particles, the particle class, so you can get with different attributes, the mass, charge number, baryon number, and a whole bunch of other things. And we also have some helper functionality. So if you want to figure out if a particle belongs to a particular category, like it's a baryon or ion or whatever else, then you can do that. We also, I think in 0.7 created particle list, which is a list-like object to contain these this particle information. And instead of getting a single value for the proton mass, you can get a quantity array, which is pretty handy. So you can do vectorized like functions on using particles. The next one is Plasmapi.formulary. And this subpackage is our biggest one and contains a lot of functions to calculate fundamental plasma parameters. And this also is based a lot on AstroPi.units. So if you want to calculate something like the alphane speed for plasma at 1 AU or the gyro radius or plasma beta, this is where we can go in order to be able to do that. All right, so as I mentioned, we're hoping to release Plasmapi 0.8 fairly soon. And there are a bunch of new features in it. We have two students from the University of Delaware working on implementing two fluid dispersion relationships for plasma waves. And this is in addition to one two fluid dispersion relationship that is already there. So these are ones that use different approximations for different regimes. An undergraduate working with me has been working on a prototype null point finder. So if you take a grid of 3D magnetic field vectors and position information, then the goal is to find where the locations where the magnetic field equals 0, which are important for things like magnetic reconnection. We also had a contributor add a plasma calculator app. So this is something where you can run it from the command line and it'll open in your browser window, and you can use it to calculate a variety of plasma parameters using Plasmapi.formulary. And so this is pretty new. It's not in 0.7. And we're hoping to do some user experience testing in the near future to get it to work. We also have some Thomson scattering modeling capabilities, and this is more for especially high energy density plasmas. Also did some reorganization of the formulary. So we broke up parameters which had gotten to be like 2,000 or 3,000 lines and split it up into speeds.pi, lengths.pi, frequencies.pi, and so on. We also have a few getting started example notebooks that are being added. So we added one on AstroPi.units since a lot of our package depends on it. We have a pull request that is almost ready to be merged for Plasmapi.particles. And then one of my goals for Wednesday is to work on a notebook for Plasmapi.formulary. So something that would like calculate plasma parameters in the heliosphere. So this is one example of a two-fluid dispersion relation solver, and this is the one that is available in 0.7. And so you can see how the propagation speed depends for different modes, depends on the angle for that. And there are two new dispersion relation solvers for cold plasma waves being developed. We also spent a lot of time making improvements to the package infrastructure. We created some typing constructs for Plasmapi.particles inputs. So something that is particle-like would be an input that can be transformed into a particle. And that was part of an effort to refactor the decorator that processes particle inputs. There were a few computationally intensive applications of the formulary. And so we worked on creating a light function framework. So these are functions that don't use quantities, but rather NumPy arrays. And they're decorated with numba.jit. And so you get just-in-time compilation. And I see Sean in the chat, go typing constructs. Yes, definitely. We also worked on expanding the project glossary and bibliography, which I think both of these were new in 0.7. And we've been implementing them more throughout the package. They're pretty handy, and Sphinx has some tools that are really helpful with that. We also were able to apply some automatic refactorings from relatively new tools like Sorcery and PyUpgrade. And then we added some more continuous integration checks, including one for code spell, and then a whole bunch of Sphinx, Flake8, and pre-commit extensions to the CI. And we're also continuing the expansion of the contributor guide. So our goal with our contributor guide is to provide a place for new contributors to stop by and learn how to contribute to different aspects of the package. So how to write tests, how to run tests, best practices for testing, how to build documentation, the different tools that are used, like Sphinx and restructured text, and then some documentation guidelines. And this is to address the challenge of onboarding new contributors. We've also been creating working groups to work on different Plasmapi subpackages and functionality. So our two most active ones are on diagnostics and dispersion relationships for plasma waves. But we also hope to form a few new working groups on things like plasma education, plasma simulation, transport for a whole bunch of different regimes, but especially things like tokamaks and fusion plasmas. And then also expanding the regimes that have functionality, that we have functionality for. So ranging from high energy density plasmas to low temperature plasmas. And if you're interested in joining or starting a working group, then please let us know. I do want to mention a few of the challenges for Plasmapi, and this slide is probably the same as it was in the fall. The biggest one is building a community of users and contributors. And along those lines, we also have to change the culture of the plasma community. In astronomy and heliophysics, there's more of a culture of open data and open source software development. But in plasma science, fundamental plasma science, fusion energy sciences, not so much. So we're working to change that. We also, like, one of our biggest bottlenecks in development is code review. We have a limited number of people who are doing the code reviews. And so some pull requests, especially larger ones, can end up in code review purgatory. And then also the data environment for plasma science. We don't have a community-wide portal for plasma data sets akin to the Virtual Solar Observatory, and we lack metadata standardization. There are a lot of ways to be part of the community. We have office hours on Thursdays at 3 Eastern. We also have our community meetings Tuesdays at 2 Eastern. And we have an Element chat room. Please request new features and share ideas on GitHub. It really ends up helping out with the project. We also have Plasma Hack Week coming up from July 11 to 15. And this is based off of Astro Hack Week and a whole bunch of other hack weeks, and is our second one. And we're still in the process of learning how to have these, especially since they've been virtual, and that adds in a whole bunch of other challenges. Then, of course, we invite you to contribute code and things like that. And there's also a link, a scheduling link that you can use to schedule a meeting with me if there's something that you'd like to talk about, and I'd be happy to talk with you about it. I want to bring up a couple of example notebook ideas. So one would be plasma parameters in the heliosphere. So that would be doing something like comparing plasma beta in the photosphere, chromosphere, and corona. And for the photosphere, a sunspot region versus more quiet sun. And then perhaps something like compare space plasma length scales at 1 AU to Earth's radius. One other one which I'd like to do would be to calculate the gyroradii of solar energetic particles in cosmic rays. So if we take a characteristic magnetic field strength of like the heliosphere or interstellar medium, we can plot the gyroradius and see where the gyroradius ends up being comparable to the size of the heliosphere or the ISM. And at that point, the particles will be no longer confined. But one development aspect that needs to be completed, which we should be working on soon, is making gyroradius relativistic. And then also I'd be very interested in working on a notebook for ionization states in space plasmas. So if we get ACE or Ulysses composition measurements, which just really say how much of like iron is at different charge levels, ionization levels, and then do some visualization, like look at how the charge states of iron differ between the fast and slow solar wind. So these are, the goal of these is to introduce Plasmapi at the same time as talk about some really cool plasma physics, heliophysics stuff. I did want to mention another package which is currently under development for the analysis of data from the X-ray telescope on XRT on the Hinode spacecraft, and Joy Velasquez is working on the bulk of the functionality. And in our initial release, there will be functions for the effective area and the temperature response function. And we're hoping to have version 0.1 released fairly soon. And if you'd like, you can check out the repo. And we've actually been having some discussions akin to those that are in the chat about how XRT Pi and other packages would be supported after mission funding ends, hopefully a long time from now, but something we still have to consider, and are hoping to do that from early on. And then I also wanted to mention a few tools that I've learned about recently that are particularly of interest to developers. So one is Nox, which it's like Tox, so it's something you can use to run tests and set up testing configurations, but it's written in Python. Codespell is a really neat thing to check spelling in source code. So it doesn't look for, so it takes a dictionary of common misspellings and looks for those instead of looking for whether collections of characters are in a dictionary. So it works pretty well. And there's Poetry for packaging and dependency management, Click for creating command line interfaces, PyUpgrade for automating syntax updates to newer Pythons. And then also some tools like Sorcery, which do automated refactorings. And there's also Mist NB. So Mist is a version of Markdown that has a lot more it's a lot more powerful. And this is it's still in the beta stage, but it's a way that you can create notebooks using Markdown as examples and get links to different code objects in there too. So it's worth checking out probably 6 months to a year from now. And then I also wanted to put up a bunch of Sphinx and Flake8 extensions also. And feel free to take a screenshot of this, and I'm happy to talk about it later, but done a lot of research into this recently. And if you look up the, I put the presentation slides into the meeting Google Drive directory. So you can check out the links for those there. All right. That is what I have.
Awesome.
Any questions?
Thanks, Nick. Looks like we've got one from Rebecca.
Maybe I'm talking too much already. Although I
please go for
posted
it.
something in the chat, and I had two other things that came to mind while you were talking. But I'll leave the thing I posted in the chat because that's a larger discussion. And I don't want to take away presentation time. The second thing's a simple thing. So you were talking about charge states right here on the bottom with ACE data, ACE and Ulysses data, and presumably you would also include wind and some other similar instruments. But so I know that at least with ACE data, they don't report the higher level charge states after, what was it, 2011 because of the instrumentation thing. So I wanted to point you to something that a colleague of mine worked on. She, Dimitra I'm going to butcher her last name, Dimitra Katrumpa, found some empirical relationships for the newer ACE data based on the older ACE data for some of the higher level charge states. Maybe it's worth that finding a home in your code. If that's interesting to you, I can point you to the papers. I will admit to being a co-author.
Okay.
So there you go. So the first thing that came to me though is when you were asking for education projects, there is a push right now from NASA for such things, even in heliophysics. The acronym HEAT comes up to me, and it's a program hosted in, I think, by Arizona State University. They might be worth contacting. There's a heliophysics subject matter expert as part of that project, and then there's these science education, like the interactive science education websites that they don't have anything for heliophysics yet, and this might be something interesting to pull up. The website starts with an I. That's all I got off the top of my head. It'll come to me in a minute. If you want, I could post that in the chat. But so maybe look up NASA. Oh, it's NASA HEAT and NASA SCOPE. That was at AGU. Are you interested in these links, or do you want to look them up yourself?
If you could post them in the chat, I think that would be really helpful. With
I'll
regards
make a
to
note.
the
I'll make a note and do that.
Awesome. With regards to the ACE data, we'll probably, this is probably not going to be a particularly in-depth notebook, but more one to demonstrate. So I think we probably use data from earlier in the mission. But with that said, we could put a link to that in the, like at the end, and say that if you're using data from ACE after 2011, then to look at those papers.
Okay, if you wish, I don't particularly care. But if you're gonna have a user using it after 2011, just copy the note from the ACE website and just at least post that at the end. That'll be more, I think, more useful to the users. Like, yeah, this data's crap after this year. Don't use that. ACE said so. Don't blame me, right? All right, I'll let other people talk.
Cool. So yeah,
Thanks for the question.
If you'd like to work on, especially the first of these notebooks, maybe the third, during the hackathon on Wednesday, then please let me know.
Quick question from Will before we move on.
Hi, Nick. I had a question about your XRT slide for the temperature responses. How are you computing the temperature response? Are those just tabulated from somewhere? Or are you folding the contribution functions through the effective area and going through it, that whole song and dance?
We're pretty much using lookup table. So we're not trying to recalculate stuff from the county database, but rather using some assumptions regarding that. So we're taking a simpler route with regards to that.
Okay, but it's a lookup table like from the contribution functions, not just the tabulated temperature
I think
responses.
so.
Okay.
Yeah.
Okay. That would be, well, I asked because the AIA Pi does right now, there's not a solid plan for how to do this. And of course, there's a problem of calculating the contribution functions is slow. And so having something in between the tabulated, just tabulated responses and the full calculation, something like a lookup table like you're describing would be very desirable. And I think there would be like basically complete overlap between our two approaches. So it would be interesting to see what you all are doing on that front.
Yeah, we should talk more to make sure that, so probably have Joy in the chat and then also Kathy Reeves to try to get on the same page for that. But yeah, we were hoping to reach out to AIA Pi fairly soon.
Okay, great. Yeah, that would be awesome.
Awesome. Well, thanks again, Nick.
Yep, thank you.
Yeah. Looks like next up we have John Niha with a Spacepie update.
Yep. Let me try to get the right screen on here. All right, we seeing that okay?
Yep.
All righty. I am going to fly through this rather than like read release notes to you. So please, I can't actually see hands very effectively. So please do, if you have a question on something, please call out or have Julie, you can keep me honest. So just give you a quick refresh around what this is since our last update was August of 2020. Spacepie is PSF licensed. We've actually been out to the public for just over a decade now, which is pretty awesome. We consider ourselves mid-level. This is not really something where we're looking to have a single integrated environment. We're trying to provide toolkits and libraries for folks. And really our focus goes from MI coupling out into the heliosphere. And that's large because that matches the research interests of the developers. So we're not really going to the surface of the sun or the surface of the earth, but kind of in between. And what we develop is really driven by needs. So that's science requirements and data set productions. But that doesn't mean it's just our needs. If you've got something you're working on that is within that domain and either have a piece of code or think you need a piece of code that's relevant, please do drop us a line and we can help provide a home. So just skim through, we've had 3 releases since that last update. So there's some good stuff I want to just point out to people. I overhauled time end to end, which means that it's a lot more consistent. We're usually using TAI underneath. So things like our Julian dates are, an extra second long if necessary, that kind of thing. We now also have support for going in and out of AstroPi time. So that lets those two systems kind of hang together and opens up a bunch of stuff. Quick little update to our UrbanPi handling, which is if the underlying Urban library doesn't handle the coordinates you hand in, we'll do the conversion for you. That really took longer than it should have. The 023 release, which was last fall, Antoine Brunet submitted support for sparse records in PiCDF, so that's nice. Did a little bit more tweaking of those time updates, including the god-awful rubber second era. If you don't know what it is, don't ask, you don't want to know. The only thing is I advise if you're ever doing anything with time and care about things to more than a minute, just get onto a continuous time base like TI or GPS time. Coordinate support, we also now have AstroPi to and from. That's Albert Shea submitted that. So that's pretty awesome because again, that connects us out better to the broader ecosystem. And some backend type stuff. So setup tools changed some stuff around that we fixed. We've got better pathing of libraries on Windows. And some folks are having issues with the .spacepy directory, like in containers and such. So we made that a bit happier. All right. And kind of as preparation for the summer school, we just did the 030 release. And there's some good stuff in that. We now have a pure Python backend for coordinates that Steve Morley put together. The speed's pretty much comparable, but the precision's a lot higher than using Urbum. And of course, that means that you do not need Fortran anymore if you're just doing coordinates. We're still supporting that Urbum backend, and we're basically doing a deprecation cycle to encourage people to move on to that Python backend. Some of the stuff, like if you're actually tracing a field, that's still based on Urbum. We're just doing the transforms. But there's also this separate IGRF module, which might be of interest to people, even if they're not doing coordinate transforms. Little stuff in UTF-8. NASA basically declared that they were going to redefine all CDF constants as UTF-8 instead of ASCII. So we did that. So you can put smileys in your CDF data now. And we're also in the middle of a migration cycle to using version 3 CDFs and TT2000 if the user doesn't specify otherwise. Because at this point, hopefully most people are on to newer libraries. Quick update to A9 AP9 for those who care about that. There's a new ephemeris file, so hey, we've got that supported. Then a couple of big projects that I mentioned in passing on the last one. One is DB processing. I did give a full update to the monthly meeting on this, but this is a separate project that is meant to basically manage data processing and coordination needs for a mission. So that's there. If you're interested, please poke me. And this summer, John Vandergriff put this effort together, which is a data model adaption thing, where we're going to try to make it a lot easier, no matter what library you're using and what data object you use, make it just easier to bounce around between them. And so we're going to do a couple of sprints this summer to really bring that home. A couple of bits of publications that we've done using Spacepie. Again, we're continuing to get the Parker ESIS data going, so we're up to 12 releases now. That's all Python from end to end. There's a space weather, space climate paper using Spacepie for doing a statistical storm production. And this is, you'll note this is not actually one of the Spacepie authors who did that. So it's nice to have people using it. There's advances in space research paper with some of the first results from a CubeSat. And finally, Dan Willing had a space weather paper with modeling the magnetospheric response to extreme ICME. And this is actually going to be part of the tutorial. I guess it's 2 weeks, but for the summer school, that'll be an underlying one of the tutorials to do. Just to do the numbers real quick, we've had about 440 commits accepted to master, which we're actually in the process of renaming. We've had 8 contributors, 4 of which are not regular developers. So that's been fantastic. 97 issues open, 69 closed, 76 PRs open, 78 closed, and 3 releases. And we're moving more towards that 6-month release cycle that we really want to do. So stuff that's coming up pretty quick. Again, that 3D space weather modeling framework support is in place. Right now we support 2D slices, but Dan's working on the full 3D support, which should be coming soonish. We had a neural net based Lstar and last closed drift shell model, which was using FFnet, which has now more or less collapsed in terms of installability. So we removed the FFnet version with 0.3. 0.4 is going to have a NumPy-based backend, which is the actual same model. It's the same it's the same neural net. It should give the same results, but faster and without Fortran. And Aaron Hendry kind of got the ball rolling on that. And Steve Morley has been bringing that across line. So that's great. We're continuing to do that coordinate migration of moving that default to Python instead of Urbum, and hopefully moving to more coordinate systems. So moving out from into the heliospheric coordinate systems. A few little things to PiCDF, beating my head against the M1 Mac. Calling conventions are fun. Some more documentations and workarounds for things that people tend to trip over. Broader terms of future, we're almost done phasing out Python 2 support and distutils as well, since that's going away. And then we're going to be focusing more on delivering more binary wheels. So the Mac wheels and mini Linux wheels, because we can see that people are going that way. And we'll probably start stuffing more stuff into the binaries where we have binary dependencies. And we will be restructuring the documentation based on the deep processing experience. If you kind of want to see how we're prioritizing stuff, we do that in GitHub projects. So we grab our issues and stuff from there. But otherwise, always do keep an eye on the issues and the PRs, because that is how we do our work. So I'm going to stop the share so I can actually get a screen back I can see, and I can see if there are any hands up.
Any questions for John?
Sweet. All right. And I did upload this to the drive, by the way. So.
Oh, perfect. Thank you.
Alrighty.
Pete, we've got a question.
Yeah, this might be a naive question, but I'm curious how the different packages play with each other and what the philosophy is. Because I've not really used Spacepie at all, and I'm wondering how much overlap there is, say, with PiSpeedus for the reading in of the data and the plotting capabilities that are in there versus what's in Spacepie. And can I use them together? Can I combine them?
So that's what we're working on with this data model thing. And PiSpeedus was the odd man out on that one, but I know they're doing work in connecting with a lot of the other ones. And that was literally just to keep the scope of that work in. So yeah, the goal here is to have these things work together.
Okay.
Okay. Unless there are no more questions for John, we can go ahead and move on. I believe next up we have a Senpai update with Stuart presenting that.
Hello. Well,
Hello.
let's see whether this works. Hey. Yep. Just going to go through things that have happened in Senpai land in the last 6 months or so. Oops. If you want to see the slides and have them magically update by the power of the internet, you can go to that URL. Senpai, for those of you who don't know or have maybe forgotten, is a core library that's existed for a long time, and a set of affiliated packages, some maintained by the same people who maintain the core library, and some maintained by other groups, and some various other infrastructure. Nearly gave me a heart attack. We've since the last one of these PyHC meetings, we've had the 3.1 and 4.0 releases, although I'm mostly going to focus on what's new in 4.0 in this meeting. We had 29 individual contributors to the last release of this core package with 182 merge pull requests. And also the other thing that's happened in the last 6 months is the 2.0 release of NDCube, which is a major update. I'll get back to that in a minute. Just first, if anybody's interested in SunPy, discussions around like long-term planning, design, general project organization, we're planning a hybrid coordination meeting in August. If you want to come in person, it will be in Dublin. If you want to attend online, that will be possible as much. We'll do as much as we can to make it both work. More information is on the main SunPy website. Okay, so things that happened in 4.0, the biggest feature by a long way in 4.0 is we mainly arbitrarily redesigned how we handle our affine transforms. The affine transform code in SunPy is used to rotate and align images against using or not the metadata provided by map. We have the big change here was kind of factoring out. Before, we had a situation where you could use either scikit image or SciPy implementation of the affine transform function. Now we have a pluggable system where you can register an implementation of an affine transform using a decorator, and that decorator can handle making like smoothing out the differences between various affine transform algorithms, such as handling nans and clipping and all of those things, which I think also meant we changed our default from scikit image to SciPy. And finally, we added a significantly faster implementation using OpenCV. So if you have OpenCV installed and want to rotate your maps in SunPy using OpenCV, you can specify that as a keyword argument. There were various other tidy ups and deprecations as we move some stuff out of SunPy core and into the affiliated packages. You can see all of these in the release notes accessible from the main SunPy documentation. NDCube, for those of you that don't know, NDCube is a SunPy affiliated package which aims to provide a base data class for holding multi-dimensional data with WCS coordinates. So that's coordinates provided by a functional transform. The big change in the 2.0 release was we moved from just using the fits specification for WCS to using the generalized WCS API developed by AstroPy. This means you don't like the NDCube is useful to you even if you're not based on a fits file. If you have a function that transforms your pixel coordinates to well coordinates, it's quite easy to get started with NDCube and keep your coordinates in that function, like do the highly accurate or whatever properties of your functional coordinates are. The main changes are lots of simplification provided by swapping to that WCS API, changes to how the extra coordinates works, and a much improved crop and crop by values methods, which lets you get subcubes out based on well coordinates. Lots of other things that I won't go into in too much detail, but if you want to read about it, you can see it in the NDCube documentation. There's also a section there on the differences between NDCube and other things like XRT, which some people might find interesting. One of the other things that's been going on is a SunPy HDE grant from a few years ago. finally managed to hire a developer, and they're currently working on improving how the SunPy time series object is represented in HTML, which is used by default in Jupyter notebooks. So this is a Fermi time series on the right here, which when you print the object in the notebook shows the different channels and various information about the metadata stored in the time series object. Other news, we won a NASA grant under the Open Source Tools and Frameworks and Libraries program. This includes money for technical infrastructure, for standardizing things between the different affiliated packages, specifically the ones maintained by the SunPy core team, so that we can make a change to the packaging infrastructure in one place and have it roll out everywhere, and various other things. You can see more details about that at the proposal. And also there's a blog post linked to here, which details all the things that AAPI, another one of the SunPy affiliated packages, have been working on for those who are interested in AA data. Finally, we're hoping to do some tutorial/example development using SunPy and other PyHC packages over the next couple of days. If you have any ideas of good things that we could do, workflows you have that involve SunPy, then let myself or Laura know. And finally, if you want to get in touch, we have a Matrix chat, mailing lists, Twitters. We also have the Open Astronomy discourse that I didn't link here, but I'll update the slides. Anyway, thank you.
Thanks, Stuart. Any questions?
So this is Joe Plowman. Can you hear me all right?
Yep.
Yep.
So I have a question / maybe feature request. There are a couple of really cool projects like Carnets and Jupyter Light, and they let you run the whole Python stack, including Jupyter and everything else, either locally and completely in a browser, which is really cool. Like if you want to do stuff on your iPad, which has a number of restrictions. They currently don't work with SunPy though, because there are a couple of packages that don't have pure Python wheels. Looks like they're Yarl and Multidict. I think it'd be really cool if there could be like a SunPy subset that works with this stuff and doesn't only has pure Python packages. I don't know how feasible that is, but
I think it's reasonably unlikely that SunPy is ever really going to work with pure Python dependencies, because we depend on.
Right.
I assume that these things pull in some of the compiled SciPy stack for you to even really be asking this question.
So this works. It works fine with SciPy and AstroPy, I'm pretty sure.
Okay. I mean, send us some links for the things and I'll look into it. But I mean, obviously, like AstroPy is something like 20% C code, and obviously so is NumPy and stuff. So I'm interested in what exactly the technical restrictions are, whether they're special cased or whatever. Yarl and Multidict, I'm going to go ahead and assume are coming in as they're transitive dependencies. They're not, I don't think they're directly SunPy from memory.
Mm-hmm.
I don't know. I mean, feel free to open an issue on the SunPy repo and we can run it down with you or something if you like.
Sure. I did just check, and actually I can show my screen. Maybe that would be helpful. I was able to pull in both SunPy and AstroPy, I believe, and it worked fine. Or not SunPy, SciPy and AstroPy, and it appeared to work fine. I haven't gone any deeper than that, so maybe there are other issues further down.
Okay. Sounds interesting.
Hi, Stuart.
Any other?
John
Oh,
D.
go
here.
ahead.
Yeah, I put something in the chat, but I'm wondering if people are, if is NDCube fully disconnected from the rest of SunPy? I mean, could people use it for other types of images? And is anybody doing that, like for planetary?
Yeah, NDCube doesn't depend on SunPy anymore. That was one of the things that changed in the 2.0 release.
Okay.
AstroPy are using it for 1D spectra or collections of 1D spectra in their SpecUtils package. And there are plans afoot to use it for radio data cubes, like space-based time radio data. I don't know of anybody using it with like planetary surfaces or anything outside of AstroPy data, like Astro data. I mean, you could, but I don't have an example.
Okay, yeah, I mean, a lot of the planetary folks already have their way of registering pixels and so forth. And the way even that it gets talked about as world coordinates, I'm not sure that's universally the way other people talk about it. So, but I was just curious because it sounds like it's pretty general.
Yeah, it is. We try to make it as general as possible. The fundamental difference between NDCube and X-array, at least last time I looked in detail at X-rays, with X-array you supply arrays of your coordinates, and in NDCube you provide like a function that transforms between your world coordinates, whatever they might be, your physical coordinates, and the pixel indices in your array. Okay.
Yeah, thank you.
Any other questions for Stuart? If not, thanks again, Stuart. Next up, we have PySat update from Russell.
All right. Hello, everybody. One
Hello.
second, let me click some buttons here. All right. Hopefully that's coming across.
Yep.
Cool. All right. Thank you for the opportunity to share an update on PySat. So we are pretty close to a release of PySat and all our associated packages in the PySat ecosystem here. So PySat, for those of you who may not have heard of it before, is a Python satellite data analysis toolkit, and it's this generalized package to make it easier to work with all kinds of different data sources. So a bit of just general package news. PySat was accepted as an affiliated package with NumFocus a couple months ago or so. So we're pretty excited by that and hoping to spread PySat to further in space science, but to communities outside space science as well. So cool. All right, that's not. Okay, so a quick summary. PySat builds upon X-ray and Pandas to create a versatile data workflow. Basically, we're trying to abstract away all the challenges of file and data handling so that scientists and other users can just focus on what data analysis that they want to do and not have to worry about the rest of it. So the whole point is to try to enable robust data independent scientific or other data analysis with a consistent, easy to use interface. So there's two main abstractions that we have, or objects that PySat presents. One is the instrument object, and that represents like a single data set that you're working. It's a generalized, links to any data set. But analog is kind of like a single audio track for recording applications. But basically you can load data. There's plugin support. So PySat is the general user interface, and it presents certain coupling functions that other developers can couple into so they can add their data set to PySat. So developers can have their data loaded into Pandas or X-array depending on their dimensionality. PySat also tracks metadata for both Pandas and X-array, so it's consistent for both. You can load things in a variety of ways. There's all kinds of different iterations that we have, including on-the-fly orbit determination and iteration. all kinds of custom functionality, because that's what science is, right? People, there's the data in the file, but as it gets loaded, or for other things, developers may need a variety of custom functionalities, and we make that possible. And it builds, instrument independence. And then on top of that, we're working on a constellation object, which is a collection of these instrument objects. So we can take that same type of ease of use and apply it to multiple data sets, because that's where we're probably going in space science, as we collect a variety of space-based and ground-based and models and all kinds of things together into an analysis to make progress. All right, so that's kind of the overview. In a general sense, here's a little bit more of a specific overview of the PiSat ecosystem. So PiSat sits here in the middle. It's the main user interface to all these different data sets. And then packages over here, from PiSat space weather up to PiSat models, they provide and plug-in support for a variety of different model or observational data sets. So if I start with PiSat NASA, this is a collection of instruments from NASA, downloaded primarily from CEDAWeb. So this would be like ICON or GUVI or CNOS, Dynamic Explorer, stuff like that. So we have a collection of routines that are optimized for CEDAWeb. We could in principle have a general support for any instrument there, but right now we have it set up so that we'd like a user of that data set to come along and couple that into PiSat, so they can make sure that all the small or big issues of the data set are handled appropriately or documented to user. For the user. PiSat CDAC provides a similar type of support, but for data sets from the Cosmic Data Analysis and Archive Center. So this is like the Cosmic 1 and Cosmic 2 constellation missions. There's some other ones. PiSat Madrigal, this uses the Open Madrigal or Madrigal Web Package. I can never remember the name. Sorry. But it provides access to all the NSF data that's served up by the Madrigal database. All right. PiSat Space Weather is a collection of space weather indices. So this would be like KP, DST, F107, things like that. So these come from a variety of different providers, and there's a mixture of existing data sets or predicted coming data sets, or some of these indices are initially released as a preliminary status and then further on released to like a more official thing. So we have multiple tags or different subgroups within each parameter, kind of reflect use in space science. PiSat Models provides access to a few model data sets. Right now it's TIGCM, SAME2, and something called DynaOS, which is a generalized database modeling thing that I've been working on myself. So PiSat Models provides plugin support to load all those different things, but it has a variety of functional routines in there to make model and data comparisons possible. So this would be like interpolations and things like that. PiSat CDF, this has just had a new release, so I'm kind of resurrecting some of the CDF support, well, for performance reasons, really. And then I'm going to have a talk on PiSat missions coming up later in this thing. So, but this has just had a release. So this is about, science doesn't actually start with a data set. First, you need a mission, and to get a mission, you need a proposal that gets funded, and those proposals require all kinds of support. So that's what PiSat missions is, to help support those type of proposals, or even, eventually support the actual ongoing operations of a mission. PiSat Seasons is a scientific analysis. So this is an instrument independent bin averaging. So you can have a 1D or 2D distribution of little bins. And then within that bin, you can have n-dimensional data that just gets averaged together appropriately with very little work. So this can be used to produce, thousands of papers where you load and process data over some period of time and all group it together. Also has like occurrence probability and other associated analysis routines. And this is actually built on the PiSat constellation object. So you can throw in a whole bunch of different data sets at one point, and it can handle all these things pretty appropriately. Okay, so that's the PiSat ecosystem. There's some supporting packages. OMMBV, this is a magnetic basis vector package that I've written. It's not directly a PiSat package, but to couple its outputs into mission operation or to mission files, it actually uses that PiSat for that coupling. And that's being used specifically on the ICON and Cosmic 2 missions, where the outputs from OMMBV end up in these public files for science data analysis. Okay, so what are some of the things that is what are the new features that are going to be coming out on the new PiSat? So the biggest one is improved NetCDF support. So I've actually used PiSat to make the NetCDF4 files distributed for the ICON IVM mission. I'm also used PiSat for the Cosmic 2 IVM files. But for those files, when I made it, it was kind of, I'm very familiar with PiSat as originator and all that. And I use the fact that, you know, I use that familiarity to have specific support for these files when I made them. I've taken that experience and now I've generalized it and made it more public so that everybody can have the same access to those things so they can make their own files, whether it's for C2Web standards, which is like some combination of ISTP and SPDF or something like that. For NetCDF files, there's a few things that you got to take care of. So set up a variety of features to make that possible for people to support any file standard, not just C2Web or anything like that. So you can just make a file by default, super easy for any user to understand. But if you're working for a particular file standard, then you can read or write those files now. Got a whole variety of functions to enable that. And now there's consistency across files for both Pandas and X-Ray. So that's really important. We also have better support for the metadata. Previously, you would just get attached to the instrument object. Now it gets attached to a particular place. And now it's all nice and compact and then there's no potential issues. Other things we've improved file parsing. PiSat actually needs to know about what files you have on your system to support iteration or downloads, or like PiSat has a function that will download updated files. So it needs to understand what files you have versus what files are on the server. So it can do comparison and download, you know, the new stuff. So I've improved support for parsing delimited or fixed width file names. File name standard support, you know, has varied over the decades, and even with new file names, if somebody says it's delimited, it may not actually satisfy the most strict interpretation of a delimited file name. So these two functions kind of have a little bit of a broader functionality than than fixed width or delimited would might imply. But these are more general than they were before to handle more cases and more instrument files. And now we can also parse out custom user tags, not just data or other information. So turns out this is, there are a lot of different things encoded in file names across missions. So we need a lot of different kind of general ways to deal with these things in a way that's easy for the users. In terms of performance, improve things like the metadata processing. It's now vectorized and things like that. And then there's a whole bunch of quality of life improvements where, you can look in the change log, but it's a lot of bug fixes, documentation expansion, unit testing expansion within PiSat, better unit testing for the plugin modules at the instrument modules that provide data support. So users making those things, they don't actually have to write their own unit test, it just gets tested. This is just kind of a visual slide, but PiSat has been funded for the past few years as part of a DARPA project via the Naval Research Laboratory. And PiSat is being used for this next generation space weather system in NRL. And as part of that, we've kind of bridged the gap between the research to operations. So there's a lot of just internal stuff, a lot of robust checks, deprecation warnings, other warnings, all kinds of logging, stuff like that, and application of. So there's been development and application of PiSat in operational settings. So it's just more robust and more dependable, and our development process is release process hopefully reflects all those things so that you can feel confident building upon PiSat that we're not going to pull the rug out on you or anything like that, and it's going to work as we say. So that's pretty good. So upcoming. I can't see what the title is. What actual upgrades have occurred? So all packages are getting an update. So far, PiSat CDF was just released at the end of last week. So this is provides fast loading of 1 and 2D CDF variables. So it's really much faster than loading these things kind of via Python, like 60 times more or something like that. So kind of re-releasing this package and got it brought up mostly to modern standards, and it's just for performance reasons. PiSat missions also something that was just released, and it allows people to generate and propagate orbits using PiSat. So you can put in like 2-line elements that are provided by NORAD, or you can put in, I've got an inclination of X and an altitude of Y, things like that, and it'll generate an actual appropriate physical orbit, and you can move that forward or backward in times if you want to. And that's a plugin into PiSat, so it's the same user interface that you would use for any other data set. And then there's going to be a talk on this particular package later in this conference. PiSat models, a new release, an initial release is upcoming. Like I said, it's got support for like TiGCM, SAMI2, and DynaS, and a bunch of model data comparisons, direct or interpolated. New releases for PiSat NASA is coming out. There's going to be more supported data sets. We actually have our first community supported data set now from Goovy. So this is coming in from somebody from Colorado, Luis Navarro. Just showed up on PiSat and said, hey, I want to add support for Goovy. And now that's been in progress. So that's it's going to require the next support release of PiSat. But same thing with PiSat Madrigal, more data sets. So we just keep adding more and more data sets to these packages as when we can. PiSat Seasons, it was originally based on the Pandas panel. And then Pandas decided to give up on the panel because X-ray showed up. So I got that switched over now away from the Pandas panel to the X-ray data set. So to restore functionality and bring the package more up to modern standards. PiSat Space Weather, more supported data sets as well. And kind of similar for PiSat CDAC. Previously, the GPS occultation for Cosmic 1 constellation, that was loaded up into a data frame. And because that was actually a higher order data set, it's like a data frame within data frame type of thing, which does have some benefits because you can have different sizes for each occultation. But now we've switched to X-ray because that's X-rays, scales better to multi-dimensional data sets. So we've loaded up GPS occultation data into that. One downside of doing that, though, is that all the occultations now actually have to be have the same number of measurements. So it requires padding some of these occultations so it can actually be consistent across the day and day to day. But that's life, right? And more supported data sets. So previously we had support for Cosmic 1 stuff. Some of the profiles, now we have all the profile information for Cosmic 1 and Cosmic 2 support will be coming as well. So we're up to about 80 plus supported data sets. That's across like NASA Icon, we've got all the instruments, a variety of space weather indices, models, CNOPS, DMSP, Hickamarka, GNSS, TAC, the cosmic constellations. As I mentioned, Goovy is coming. It's already up. There's a pool, but it's coming from the community. We've got gold. This is just a sub selection. This is not all of them, of course. That's not 80. But there are ways in PiSat to list all those things. Okay, so we've also spent a lot of time on documentation, getting that stuff continually improved. So the whole one of the design goals for PiSat is to get people in the community to add their own data sets to it. So we've spent time on the documentation, of course, on how to add in a new instrument. And I think we've done a good job there. There's also a nice healthy tutorial on using PiSat for those that want to get started. Wherever possible, we use, we've paid attention to the formatting. So we got warning boxes, note boxes, example boxes, right? The more you know type stuff. Try to make it interesting. And for users, there's also a lot of documentation on each of the instruments. So this is a selection from the PiSat NASA package, but we've got doc strings and stuff for every single mission to introduce it, point people to the actual scientific references and all that kind of good stuff. And then, out of PiSat Seasons, we've got a lot of examples on how to actually use the methods in there, and we've applied it to some of these data sets. Okay. So that's the update that I have so far. So thank you all for the time, and any questions or comments?
Yeah, it looks like we have some questions in the chat. The first one that I saw was from Will. What are the differences, advantages, disadvantages, etc. of PiSat versus PiSpeedus? Is there a summary somewhere? I'm not sure if that exists.
Yeah. Well, I think that there's different approaches in PiSat versus PiSpeedus a little bit, but I think both are trying to provide some generalized data access and things like that. The first version of PiSat was more like a data plotter, so it had access to all the data and stuff like that, but primary thing was on the plotting. The downside I found with that is if you found something interesting because it was just a plotter, the plotter didn't really help you. If you needed to do some analysis, then you'd be forced to go and then write some new code again. So PiSat was the response to that, is it still has that kind of data plotter functionality, but rather than being all packaged up, it's present as a foundation. So it's like at the terminal you can write, it's just a more kind of like MATLAB approach where I have all these functions for you to be able to do stuff, but it's more packaged together than like MATLAB, which just everything's just there and nothing works out of the box. right? PiSat stuff works out of the box, but if you need to do custom stuff, then it's really kind of trivially easy to add new custom processing or whatever you want into it. So I can't speak directly for PiSpeedus, but PiSat's really built on being able to customize, for scientists to customize things that are going on in a very simple way and robust way.
Awesome, thanks. There are a
Thanks.
couple more questions in the chat, but I'll quickly ask. Angel, do you have a question? You have your hand raised.
Thank you. Hi, Russell. I was wondering, related with the new Git application that is going to be released in the upcoming releases. This is going to be an application running on Qt 5, or is totally development on Matplotlib backend Canvas? Thank you.
I'm sorry. So did you say Groovy or?
Git, graphical user interface.
Oh, GUI. Oh, yes. So PiSat does, I think, have a Matplotlib requirement, but in and of itself, it doesn't have that GUI functionality. Now, that's one of my plans, is to later on add that kind of on top.
Okay.
But at the same time, the Komodo package is there, and they're kind of, I don't want to speak too much for them, but one of their features is, a lot of visualization, and they're kind of like, you give Komodo data, and then after that, you just tell Komodo what you want, and it makes it happen. So my original plan was to, layer a GUI on top of PiSat, but with Komodo already kind of focusing on that, I'm kind of hoping, that they'll be able to provide that functionality, and we can just connect PiSat to Komodo. And that has kind of already happened with the PiSat Komodo package. At the time, I think our support was primarily pandas. So the coupling there is at the pandas level, I think. So it's 1D, mostly 1D data. But hopefully, in the future, we'll be able to get the X-ray thing coupled into Komodo there too. And then I'm hoping that package will provide the GUI functionality for us.
Okay, thank you, Russell.
Thank you for the question.
Awesome. Let's see. The next question that I saw in the chat was from Rebecca. She was wondering, how do the capabilities available through OMMBB compare with those from IRBEM, IRBEM, from someone new to both?
Oh, yeah. I'm not particularly familiar with IRBEM. So OMMB does have some field line tracing routines in there that I built off of existing SciPy interpolators. And it's principally coupled in DiaGraph, but I've got hooks in there so people can add any magnetic field or whatever that they want. So I can't speak to the specific integration from IRBEM, but then integration I'm doing is, kind of SciPy. That was the point. Connect the well-established SciPy code to a field model and let it do its thing. And that seems to work out well. I'm pretty happy with that as it is. And then I'm using that field line tracing for magnetic basis vector calculation. Maybe there is a way to use IRBEM instead, but I haven't had a chance to evaluate that, and I actually don't have any funding for kind of stuff like that. But yeah, if there's community interest and maybe reducing the tracing, the variety of tracing programs and stuff like that, or comparing and finding the best, I would be happy to participate.
Yeah, it sounds like an interesting way to link PiSat with Spacepie.
Sure,
If I'm
yeah,
getting my
that'd be
package
great.
names right.
Yeah.
But I'm not from either package, so I will leave it alone.
Yeah.
Fair enough. Let's see. Stuart was wondering, what are the differences between PiSat missions and Polyastro? Yeah, in terms of propagators, etc.
Okay, well, I'm not familiar with that particular package, but PiSat missions itself did not write the orbit propagation or generation. Right now we're coupling, well, originally we started with PyFM, but then we're deprecating that one. And right now we're using SGP4. And then I think there's a new one that I saw that's not PyAstro or something like that. And I'm forgetting its name right now, but it also, it looks like it couples into SciPy integrators to include radiative forcing and some other higher order effects that aren't included in SGP4, but it also includes SGP4 as a backup. So our plan with PiSat missions isn't so much to write that orbit thing, but to take packages that have that functionality and just make it usable from PySat.
I know that PolyAstro implement a bunch of propagators and stuff, so you might want to have a look.
Okay, yeah, thanks for the note. Appreciate it.
Let's see, I think I've gone through most of the questions in the chat that I found. Does anyone else have a question for Russell?
To either use the Fortran orbit propagator.
I can't remember the name of it. Darren, do you remember the name of the one that I'm thinking about? Like Katie was working with it. I don't know if Darren can speak up, but I know he's here. I'm blanking on the name right now, but that's the one that Katie and someone at Colorado Boulder is already working to pull in physics-based models into to like test that. Catherine Garcia Sage usually presents on that. I cannot remember the name of this thinking package. I'm so sorry. But I was wondering if that, in case you happen to know the name.
I don't think so. Not offhand, but I'd be happy to include all these different orbit propagators in PySat missions. I think that, that'd be great.
Ew, testing. New
Yeah.
model comparison. Okay, I'll hush.
Awesome. Well, if there are no further questions for Russell, then we can go ahead and move on. Thanks again, Russell.
Thank you, everyone.
Yeah. Let's see, the last presentation we have up for today is a Skywinder update from Bjorn Kjellstrand.
Hello.
Hi.
Hi. Let me share my screen and dive into this.
Awesome.
All right. Do you have the PowerPoint?
Yep.
In front of you? Okay, great. Hi. So I'm Bjorn, and I'm here to talk about Skywinder. I've been involved with PyHC for a few years now, but there was a bit of a delay while I was finishing up my dissertation, so I thought I would remind folks a bit what Skywinder is. This is certainly a project with a bit of a smaller scope than the past few ones we've been discussing, but it's something that I'm very excited about, and which is under some pretty active development. There we go. So Biff Williams is the PI, and I am the postdoc working on this project. Again, it's a pretty small team. Feel free to contact either of us directly if you have questions, coding questions. It's probably best just to contact me. So our goal with this project, the Skywinder project, is to create a package that's broadly applicable to various mobile aeronomy experiments, in particular balloon-borne payloads. But we think that planes, rockets, and reusable launch vehicles will also be viable. What we're really trying to do is we're trying to take the software that we wrote for the PMC Turbo balloon mission and make it available to the community, both the flight control software and our kind of preliminary analysis software, the stuff we expect everybody to be needing to use. Yeah, so I think that the work that I'm doing right now is really the first few steps in the PyHC process, the grading and uploading. This is happening in parallel with some live development that I'll discuss as well. So just to kind of create a more concrete idea of what PMC Turbo, what the software actually does, I thought I'd show a couple quick photos. So our experiment, we just hosted 7 optical imagers on a platform that floated in a balloon. Here's our field team. Behind them, and me, is our experiment shortly before launch. Basically, each of these optical imagers included a kind of server grade computer, all of which were running the flight control software in parallel. One of which assumed the bulk of the duties, but the idea is that we needed a distributed flight control system for resiliency. We launched this on July 8th, 2019, over 6 days, well, 5 days and 22 hours. It floated from the Swedish Arctic over Greenland, over Baffin Island, and we terminated the flight just south of the Northwest Passage. During this time, we were communicating to and from our ground stations, sending down both housekeeping and actually quite a bit of data. It was very compressed data. We captured 6 million-ish images, each of which were 20 megabytes. So we had no hope of possibly downlinking the raw data using our bandwidth, which was 200 kilobits per second. But we did a bunch of both lossy and lossless compression, downlinked it, and looked at that data in real time. It landed remarkably softly, just again in the Canadian tundra. So we didn't end up having to use our backup data, but we also flew a piggyback in the winter of 2019 to 2020. This is a super tiger experiment. They study cosmic rays. However, they gave us 60 watts of power and about 10 megabits per second of downlink bandwidth, and we worked with them, but basically just bolted one of our instruments onto theirs. This experiment flew much longer, for about 30 days, and circled the South Pole twice in this time. So we developed this software primarily to be very resilient and to provide us backup, because balloon-borne experiments are still risky. I mean, these happen over the Antarctic and Arctic primarily. NASA's developing also flights over the South Pacific, but you aren't guaranteed to get your balloons back. Furthermore, communication is unreliable. You can communicate both via the TDRS and the Iridium satellite constellations. And there are patterns, but you are not guaranteed full bandwidth at all. So you need something that both is autonomous, but when you are able to communicate with it, you can downlink as much backup data in the event your payload is not recoverable. We took advantage of our essentially capable computers, our server computers that we are pretty much compelled to have to deal with our data throughput, and we designed a distributed flight control software. We anticipate this will, the software that I will be publishing under the Skywinder umbrella includes our pipeline that was directly interfacing with our hardware, but I anticipate that this distributed flight control system is going to be most broadly useful for future experiments. I anticipate that somewhat because I'm working with future experiments right now. In particular, this is what we call our communicator subsystem, which basically deals with a local network, sends data to the ground, receives commands from the ground, and our ground control, which is the other side of that. It's displaying data, it's tracking all of our packets. We actually use UDP packets rather than TCP because we don't want to have to deal with handshaking. When you don't quite have a reliable connection, you basically just want to spray as many packets in both directions and hope that some of them get through. So we use the more simple UDP protocol. We also have, I've bolded these since I think they're most broadly useful. We also have controller, which is kind of interprets commands and decodes them into multi-step processes. An example is we often will do focus sweeps to ensure that we are on the most optimal camera focus as temperature fluctuates and changes exactly where that is. And then the pipeline, which is grabs images from our buffers, stores them to disk. This is just kind of a graphic showing more or less we have these various software subroutines running on each of our computers, which are located inside pressure vessels. It's close to vacuum at the altitude that we fly at about 38 kilometers altitude. So you have to, well, either have vacuum rated electronics or enclose them all in pressurized vessels. This includes our camera and our computers. And then we basically set up a local network on our balloon that had as few single point failures as we could manage, and interfaced with, again, both the Iridium satellites and the TDRS satellite, the channels. Furthermore, we include some software analysis. This is focusing on stuff that, again, will be broadly useful for groups which are doing image analysis, taking raw data, cleaning it through flat fielding. Most groups that are at least imaging with optical or near optical cameras, you have some sort of geometric distortion just because of your viewing angles. A good way to solve for this is identifying stars, finding your pointing, and projecting onto the sky. And then we have a couple more advanced features, like looking at power spectras, tracking features, and then stitching together everything into movies. I'm not going to go through all the text here, but this is just an illustration showing essentially our raw data, applying a flat field correction and removing a moving average. You can see we already get tremendously better signal to noise ratio. We identify stars, basically looking for bright points that extend slightly more than 1 pixel. These because various atmospheric effects, you have a couple pixel width due to movement and atmospheric effects. Single bright pixels are typically hardware issues, but you find those, identify them, run them through some sort of pointing, a star catalog. You find the pointing and then projecting the image. And we have a couple ways to do this, and there's some pros and cons with each method depending on speed versus resolution. But we want to project these images onto the night sky. And then we also can take these and stitch them together into movies. This is what our 4 of our cameras looks like when we look at 10 minutes or so of data. In the last couple months, there have been a couple particular developments. The first is that as part of another subcontract, I've been working with the Balboa group, which is an auroral imaging group, to help implement the Skywinder flight software on their experiment, which is great. It's a bit of a trial by fire to make sure that we're understanding exactly what other groups are going to want, and making sure that the parts of our software that we want to be modular are modular, right? They have a completely different hardware. So for example, our pipeline, which was developed specifically around that, is not so useful. So I'm trying to make our software more broadly useful. And then also I have been hosting a lot of the PNC Turbo and the piggyback data at the SPDF that NASA runs. My real hope here is that it will be a very low barrier to entry for other groups that are interested in this type of data analysis to download data, and then also download the basic functions that you always need when you're working with this data, and launch their own analysis from there. I also think we kind of just scratched the surface of this data analysis. So I think it's a pretty rich mine. But these are kind of broader long distance goals. I mean, my work with Balboa is funded on that. Through the Skywinder, I'm really trying to update the software, pass the good practices that PyHC has defined and posted on the PyHC website. Yeah, and that I anticipate will be done very soon, by the end of September. So I think that's where we are. That's what our software is. I see there's a few comments in chat, so I want to leave time to address those. But yeah, thanks for listening. Let's get into questions.
Thank you. Let's see. Rebecca, first of all, said that this needs to be a talk at AGU and AAS to advertise more and shout out to a fellow balloonist. And then she also asked, how does the star ID compare to results in astronomy star finder on a CubeSat?
So we use, I haven't used the, sorry, I guess I don't know what that means. I don't have
My
experience with
phrasing is poor.
astronomy.
My phrasing was poor, but so I converted from astrophysics over to space physics and software and those kinds of things. So here's my question, right? And I did ballooning stuff with thunderstorms, so I got a couple different weird things. But typically on a high altitude balloon, and I don't know about the rocket launches, but typically they have a star finder to be able to align their data with where the location is, because otherwise you have no idea where you're looking, right?
Right.
Particularly for astrophysics. But I think that's also going to be very true for space physics missions. So the question that you're going to get asked is, how do the results of your star identification algorithm compare with a commercially available star tracker or star finder, whatever they're called? And that would be a good test to prove your algorithm. And I also encourage you to go advertise this more at AGU and AAS. Do you know what AAS is?
Not really. Please tell me.
American Astronomy Society. So it kind of like AGU is the place for geoscience and earth science. AAS is the place for astronomy and astrophysics and even some solar physics things. So I think this, assuming you're successful, which good luck, thumbs up, encouraging thoughts, right? Assuming that's the case, I would recommend you go present there as well.
Yeah, it's definitely been interesting. So our science is covering the middle atmosphere, but a lot of our engineering is very much applicable to astronomy. Actually, our experiment kind of developed out of a cosmology experiment where their star trackers captured a bunch of very weird clouds, and that was the motivation. Those weird clouds turned out to be interesting. That was the motivation of our experiment. So yeah, it's always interesting to try to connect connect different fields that might not be talking to each other quite enough. But thanks. That's a great great advice.
Sure. Good luck.
Awesome. Any other questions? Thanks again, Bjorn.
Thanks.
Awesome. Well, that was the last talk we have for today. We will start again once more tomorrow, same time, same place, with some more project updates, introductions, paper presentations, and so forth. Look forward to seeing all of you then. Thanks, everyone.
See you tomorrow, Julie.